Hi, hello. Hello, so we want to welcome you. Sorry, we want to welcome you to our event about electromobility and territories. If I may give some quick instructions on the tool that we are using. So I'm sorry, I didn't present myself. So I'm Amira Belhamida. I'm a project manager at IRT Systemics and responsible for the circular economy and ecological transition thematic at the Technological Institute of Research Systemics. And today I'm very happy to have you and to have a very nice panel that I will present about electromobility and its application on territories. Just some few instructions of how you can use this tool that we are using. So for a better experience, please go on Chrome Navigator. If you have what I see, you have the screen in front of you, and at your right, you have some boxes. These boxes will be really useful as you cannot talk in the sessions if you are not a speaker. So you have a chat box where you can write if you have some issues or some comments, or just say hello everyone. You have the question box. And at the end of each session, we'll have a question slot, and we will try to answer your questions as well as the participants. And then you have the third box, which is the participant one, where you can see who is connected. So I think you are coming as the event is going on. Just a few words. We want really this event to be as a drawing of an up-to-date, recent state-of-the-art on electromobility and its application on territories. And we propose this program. So first, we will give the floor to Eva Pinault from la Communauté d'Agglomération Paris-Saclay to present us some challenges on the territories towards the electric mobility. The program is divided in two sessions. The first one is about vehicle fleet management, and then we'll have a small break. And the second one will be animated by my colleague Riem Kada, which is about the deployment of charging station networks. Then a questions and answer session, and then we will conclude. So each one of the speakers will have only 15 minutes. So I count on you to be there, to be on time, and to ask very nice questions. I think I'm okay. Just a few words on IRT Systemics. We are the Institute of Research and Technology, and we are at the initiative of this event as we are a hub of partners as academics and also private companies. We work on really specific domains, so mobility and autonomous transport, industry of the future, defense and security, and finally environment and sustainable development. And this is the scope of our program. We are in this domain. The boxes that you see in the middle are our competence, so our skills, our teams. We have very talented teams on data analysis, on user experience, optimization, safety, and so on. So I will not be so long. Just to introduce my first speaker, which is Eva. We work very tightly with the Communauté d'Agglomération Paris-Saclay as a territory domain with real data and real problematics. And we asked Eva, who answered positively to our invitation, to speak about the problematic. So Eva is a project leader in the energy transition department of the EPS. She's a graduate engineer, and she works as an energy and environment expert and advisor on energy issues for the local energy and climate agency in the REUR department and the Social Union for Housing. Then she led some projects related to housing and energy before becoming head of the existing housing division in the Qualitel group. She then joined the CPS in 2018, where she works as a project leader for the implementation of the territorial climate plan. Now she leads the team. She's the head of the team, and I welcome Eva. Hello, Eva.
Hello everyone. Thanks for inviting me to this event. I don't see clearly. Yes, thank you. So I'll introduce you first the Communauté d'Agglomération Paris-Saclay. It's a territory in the northwest of Essonne. So it's 20 kilometers in the south of Paris. It's an inter-municipality, so it gathers 27 towns in this department. It's a territory where the operation of national interest named Paris-Saclay is settled. So it's a huge research and teaching center settled in one part of the territory, but the territory is not only this operation. So I'll speak with you about electromobility and how we see it, how we deal with this issue in all of our scope. So how it's an issue for us, for our territory, because it's an issue about climate change, because it's a source of greenhouse gas emissions, and also it's an issue about air quality. So we deal with the climate change in general with a climate plan. So in 2019 we elaborated a climate plan to deal with the climate change. So it's made of 9 topics. We have buildings, mobility, circular economy, renewable energy, etc. And in each of these topics, we have actions in order to reach some targets. We have 126 actions in all of these topics, and some are about electromobility. And so to tell you in general what is the climate plan, it's a long-term strategy for all the territory, telling how we can reach those targets you can see. So the target is to, at 2030, to be at to lower the emissions from 34% and from 56% at 2050. You can't see the numbers, but it's 2030 and 2050. So you can see that you have the sectors of emissions. The orange one is transport emissions. So you can see that transport emission with building emissions, which are in yellow and pink, are the most emitter sectors. So we have a big issue with buildings and with transport in our territory. And transport has to be lowered by a third to 2030. So it's our big target, and it's an ambitious target because in our territory there are more and more people. The demography is growing, so it's a big issue to be able to lower the emissions where our population is growing. So if I get in this climate plan, I can show you that there is a part for mobility. So in the climate plan, there is a strategy part and an action plan part. So in the strategy part, we explain how we can do to reach our targets, acting in some level. So for mobility, there are several levels. Keeping the increase of the mobility needs under 4% when population increases by 30%. Lowering the use of personal vehicle, getting vehicles more efficient, developing rail freight, and replacing petroleum vehicles with electric, hydrogen, and natural gas vehicles. So there you can see that our first solution is to lower the use of personal vehicle, because what we want is that the needs for mobility change, and that the use of a personal vehicle becomes not a need of every day. It has to be something that that people reflect, and perhaps it's not a need that everybody has his own personal vehicle. So you can see that we aim to evolve in the modal share for commuting or for everyday life. You can see that the effort is to make people use public transport more and more. In our territory, we are waiting for the line 18 of the metro, the subway. But for the moment, public transport is more on buses. But we are waiting for rail-based public transports. So we have to lower the use of personal vehicle, using public transport, using also bicycle, but it's a little part of this. And also for vehicles, for personal vehicles, we aim to enhance the use of carpooling and car sharing, because it's what I told. It's there can be some personal vehicles, but they have to be shared, and perhaps what we can hope is that going from one point to another is with a vehicle can be a service like public transportation, and you go in a station, you take a vehicle for your move, and you take it back. But not everybody has his own vehicle. So you can see the evolution of modal share with a little part for individual car at 2050. It's about 10-15%. And in this little part of remaining needs to move with a personal vehicle, we target to change also the energy supply. As you can see on the right, the goal is that there are no more petroleum vehicles in 2050, and energy supplies would be natural gas vehicles, or hybrid, or electricity. In electricity, we include hydrogen also. So there is a little third of vehicles that would be electricity vehicles in 2050, including hydrogen. If I'm not clear, tell me. deal with this issue, our elected representative decided that we had to deal with this issue of energy supply and to help electromobility developing, because it's an innovation for the moment. So public body has to play a role in this. So in Paris-Saclay community, we decided to develop an EV charging station network in our towns, in our cities. So knowing that there are big cities like Palaiseau, Massy, Longjumeau, and very little towns with less than 1,000 people. So there is a big diversity of towns. So we have to deal with each possibility, each city. So we propose to every town to give us the right, the competence to install a charging station, EV charging stations. So 20 towns gave us the right to install charging stations. So right now there are 47 charging stations that works. 2 are being installed right now in Champlain. So we have about 50 charging stations in 20 towns. Our goal is not to be an electricity provider. Our goal is, as a public body, to comfort the individuals in their desire to use an electric car, and to make it very easy to use an electric car. Because right now everybody knows how to refuel a car, but not everybody is all right with the fact to reload with electricity a car, and it's what we want to be easy. So we are not there to be a big provider, but also to reassure, to comfort the individual, to tell it is possible to have an electric car. It's easy, and wherever you go in the territory, you can reload. So there is no fear. You can ride your electric car in our territory. So we deploy a coherent and readable network. So every charging station is working the same way. For each station, we have 2 charging points. They deliver 22 kilovolt ampere. So it's what we call quick charge regarding 3 and 7 kilo stations. It allows to reload easily some kilometers necessary to go to your home where you have your charging point. So we don't need to go further in the power of the stations. The payment is with a badge or a credit card to make it very easy. And we also managed to have the interoperability with the other mobility service providers. So it's easy for the people who have other badge like ChargeMap, KiwiPass, etc. They can, with their badge, reload in our stations without difficulty. It's our goal too that everybody can load in our stations, and it's easy for everybody. Just to little results of our network for the first year. This year includes lockdown period, so it's not a good first year, but we have 900 unique users, and we have an average of 4.1 sessions by charging point by month, which is rather good, because at a national point of view, Isivia told us that their average is 4.5 sessions by month. So our network is working rather well, and you can see that users come more and more to our stations. We can see that people get used to our network, and is that we want to see. So we can say that people rely in our network, and we heard several people telling that seeing that there was a station near from their house or where they are going, they buy an electric car. So our goal is reached, and now we have to enhance our network to respond well to the demand.
Congratulations for the community of agglomeration Paris-Saclay. Thank you, Eva, for your talk. It was quite clear. Please do not hesitate to ask questions to Eva in the question box that you have on your right. Sorry. And now I want to start the first session about the fleet management. Thank you, Eva, again. I want to welcome Emilia Suomalainen from Vedecom, which is a project leader of the shared energy team. I'm very happy to have her today among us. The shared energy team conducts research on EV, on electric vehicle charging infrastructures, and the related energy services. Emilia has a PhD in environmental science from the University of Lausanne, Switzerland, and a Master of Science in Technology from the Helsinki University of Technology, which is now part of the Aalto University, in the field of system analysis and operations researches. Emilia has been working as a project manager and researcher in the field of transport and environment for over than 10 years. So I'm really happy, Emilia. Welcome, and the floor is yours.
So thank you very much, Amira. I hope you can hear me well. And thank you very much to Systemix for inviting me to speak to you all this morning. So if I could just have my slides. Oops, sorry. So as you heard, so my name is Emilia Suomalainen, and I work as a project lead and researcher at the Research Institute Vedecom. And I would like to present to you today some of the work that Vedecom has been doing in the field of electric mobility. So to start, just a few words on Vedecom. So Vedecom is basically a public-private research institute. So we're based in Versailles, near Paris, and we're one of the French institutes for energy transition. And Vedecom is working on three major topics, namely electrification, autonomous vehicles, and also various mobility and energy-related issues. And Vedecom has over 50 members and partners ranging from private companies to universities. And in the field of electric mobility, our partners notably include car makers such as Renault and Stellantis, but also the French electricity provider EDF, among many others, of course. So to start with the big picture, as you all know, the climate change issues make it imperative that we reduce our CO2 emissions and promote cleaner energy. And this, of course, means that we need to decarbonize the transport as well as the power sectors, both of which are responsible for a major share of global emissions. So in this context, of course, electric mobility provides one of the ways to decarbonize transport by moving away from the current oil-based mobility towards EVs that would be powered by clean and low-carbon electricity. However, there are still a few obstacles before electric mobility can be adopted at large scale. And the three major issues that are cited by potential EV buyers include notably, first of all, the high price of EVs. Secondly, the autonomy that is perceived as being limited. And thirdly, the lack of charging infrastructure. However, the good news here is that all these three issues can actually be tackled by better EV charging infrastructure. So good charging infrastructure makes it possible to have EVs with smaller batteries and less autonomy if the drivers are always sure to find a convenient place to charge. And these EVs with smaller batteries would also be less expensive, as the battery represents an important percentage of the vehicle price. Of course, to make these EVs really environmentally friendly, they need to be powered by green and clean electricity. And as though the problem with most renewable energy sources is that their production varies quite significantly in time and does not necessarily correspond to the consumption peaks. So this means that we need to store the renewable energy to be used later on. And the good news here is that EVs can be taken as batteries on wheels, which means that they can provide this mobile storage capacity nearly for free, and therefore provide services to the electricity system, such as storing this excess production of renewables. So this is a kind of a win-win situation, both for the transport and for the power sectors. And EVs could provide these energy services both at the local and at the network or grid levels. So following this introduction, you might have guessed the two main focus areas of the shared energy team at Vedecom. So first of all, we look into the deployment of EV charging infrastructure. And secondly, we work on these new energy services that could provide flexibility and storage to the power system. So you can see some of our research topics listed here. I won't go into detail. I would just like to state that we employ basically a kind of, let's say, technico-economic approach. And we look at things such as the sizing and location of charging infrastructure, the deployment strategies, the costs of this infrastructure, these new energy services, different externalities, also some regulatory aspects, and so on. And to illustrate the work that we do, I would like to present to you quite briefly some of the projects that the shared energy team at Vedecom has been working on. So firstly, we have been working on a project on electric road systems for long distance trips on highways. As you might know, these long distance trips are really seen as the major obstacle to the large-scale deployment of electric mobility. And if EVs are to be used both for everyday and long-distance mobility, we need to provide charging solutions also for these long-distance journeys. So the objective of our modeling work here was to compare the costs of wireless inductive charging, which is one of the technologies also developed by Vedecom, and traditional charging stations. And although this inductive charging infrastructure remains more expensive, it would also provide a lot more convenience to its users, which might in turn justify this higher cost. So in the context of highways, we also worked with this startup called EP-Tender that's developing this external range extender that provides 300 kilometers of additional autonomy for long-distance trips. So we notably worked on simulations of the future rental network and the economics of this kind of a service. And of course, the advantage of this kind of a system is that it is a lot more flexible than fixed charging stations, as these mobile batteries would follow EV users all over the territory. And this system could also be used to provide energy services when it's not needed for mobility purposes. So in addition to this highway and long distance context, we've also been working on charging infrastructure in more urban and suburban settings. So there is notably a PhD thesis that's looking into how to position this EV charging infrastructure in a territory while taking into account the mobility needs of the people and their everyday trips. And we would notably like to study here how we can develop destination charging rather than creating specific charging destinations. And another aspect we would like to look into is how we should deploy this infrastructure over time, as it is, of course, a long-term investment. However, my colleague Marc-Olivier will tell you more about this work later this morning. And now we come to our second line of research, namely the energy services. And we've notably been looking into the synergies between renewables and EVs. And we have a PhD student, Icaro Freitas Gomez, who has been doing simulations on a coupling between commercial buildings with PVs, stationary storage, and a fleet of EVs. And he notably studied how different electricity tariffs can impact the gains for the different actors in a case study that he did for California. Of course, the aim of this work is really to explore how appropriate tariff design can be used to drive these synergies between renewables and EVs on a local scale. Also, one of our researchers did a review of all the different energy services that EVs might provide to the TSO, DSO, or to the building or microgrid manager. And he found around 16 different services. There was also a meta-analysis with the aim to estimate the value of these potential services. In addition, we have a collaboration project with EPFL where a researcher called Dirk Lauinger has been looking into how to provide reliable frequency regulation from a fleet of EVs. So Dirk notably takes into account various uncertainties in the system, so both in the presence of EVs and in the size of the grid incident. And his work suggests that with the current EU regulation, aggregators might actually benefit from promising more regulation than they can actually deliver. And last but not least, Vedecom has also been working on an innovative concept of vehicle-to-vehicle fast charging. As you know, fast charging infrastructure is quite expensive and can also have a big impact on the distribution grid. So the idea here is that a fleet of EVs could be used to provide fast charging services locally. And this would, of course, avoid these investments in reinforcing the electric grid and also be less expensive than traditional fast chargers. So to conclude, EVs are indeed one of the solutions for moving towards clean and low carbon mobility. However, this also requires greening the power system to provide clean electricity for our mobility needs. Luckily, there are some very strong synergies between the large-scale deployment of electric mobility and renewable energy. And EVs can provide both flexibility and storage services to the power system. However, to deploy electric mobility on a large scale, we really need to develop charging infrastructure that is adapted to the needs of its users. And also, as cars are a very underexploited resource, and there is a big environmental impact that is linked to the manufacturing of EV batteries, we should really maximize the utility of these batteries by also exploiting them for these energy services. However, as you know, there are still many challenges that remain before these new vehicle-to-grid, vehicle-to-home, vehicle-to-building concepts can really take off. And Vedicom is also hoping to contribute to overcoming some of these obstacles through its research. So I've listed various references for you here. Please do not hesitate to contact us in any case if you'd like further information. I thank you for your attention.
Many thanks, Emilia. Very impressive panel of projects. Really very good presentation. Please, do you have any questions for Emilia? Write them down on the questions box that you have on your right. Thanks again, Emilia. I want to welcome now my colleague, Jacob, who is responsible for the research axis of scientific computing and optimization at IRT Systemics, as well as a professor of industrial engineering and responsible for the operation management team at Centrale Supélec, and he's also co-director of the Future Cities Lab urban at Centrale Pékin. His main research interests are about urban logistics, human-centered innovation for urban mobility, disruptive technologies, and algorithmic optimization of the underlying transport systems. So Jacob is an author of more than 70 scientific publications. I'm very happy to have him today in this session. Welcome, Jacob.
Hello, thank you, Amira. I'm very sorry my camera is not working, so it's a little bit.
As we can listen and see the slides, yeah. It will be okay.
Okay, so that's great.
Yes.
So I'm sorry for that. So can I move the slides myself, right? So yeah, so I will be talking about electric vehicle fleet management and recharging. I will be very quick on the introduction. As we just heard in Emilia's talk, the advantage of electric vehicles is that they don't have local pollutant emissions. There is also lower noise pollutions. But as we all know, the overall greenhouse gas emissions of electric vehicles will depend on the energy source used to produce the electricity for powering the vehicles. And so what is actually the motivations for using electric vehicles in urban mobility? As we heard before, the range of these vehicles is now extended. Also, they are quite cost efficient. However, there is still an initial high initial investment cost. They still have a limited range. Recharging is quite time consuming, and also the recharging network is not fully deployed everywhere. So in order, that's why we need to utilize these electric vehicles very efficiently. So in the tour planning, we need to take into account the state of charge. We need to plan recharging stops, and we need to decide on the charging amount. And so that's the reason why we are very much interested in fleet management for electric vehicles. So that's what I will be talking now. So the first part, actually, I will present you a few projects I have been doing in the last years. So the first one, the first two, we have been looking at hybrid heterogeneous fleets of vehicles, where we looked at different vehicle types with different properties. So for example, we looked at fleets that are composed of internal combustion engine vehicles, plug-in hybrid electric vehicles, and battery electric vehicles. And then we looked at how to organize the fleets composed of those vehicles. So this is a paper I did with some colleagues, one former PhD student of mine, Gerhard, and some professors from Vienna and from Brazil and now Canada. So we looked at these 3 different vehicle classes, and also there is multiple subtypes of vehicles that are different in terms of their transport capacity, cost, battery capacity, and fuel consumption rates. So we developed a quite advanced method where we divided the decision process into different layers. And as you can see, the main challenge with these different vehicle types comes actually from the tour planning part, so how to organize the tours. So with the internal combustion engine vehicles, this is quite classical, and we know how to do this. With the battery electric vehicles, this is, I would say, research from the last, I would say, 6 to 10 years on how to organize tours with battery electric vehicles and where to plan recharging stops. So here the triangle you see below the battery electric vehicle tour is the recharging station. But with plug-in hybrid electric vehicles, we have an additional decision part where we need to select the mode whether to use electric energy or fuel. And for example, in our vision, we preferred to use electric energy whenever it was possible, and only when it's not possible. For example, here when we go to the recharging station, we ran out of electric energy, we had to use fuel. And the planning of this switching between electric energy within vehicle tours is quite challenging. And so that was one of the main research topics we looked at in the method we have been developing. And what we saw when looking at the results for the fleet composition is that when we compared pure fleets, so pure fleets with different cost, electricity cost and fuel cost settings with the mixed fleets, we saw that except in extreme cases, so when we have very low fuel costs or very low electricity costs, the mixed fleet is always performing best. So depending on your cost structure, of course, you might have extreme cases where using purely electric fleets is better, or purely fuel-based fleets is better. But in I would say intermediate cost settings or average cost settings, using a mix of electric and battery electric vehicles and plug-in hybrid vehicles gives you the best results. And so that's more or less the summary on this first project we did. So that these different fuel and energy price scenarios have an impact on the optimized mixed fleet. And what we see is that the operational cost of the best mixed fleet can be up to 77% improve on homogeneous fleets, depending on the cost settings. And what we did then, we got interested on on how electric fleets and sorry for that, on how electric fleets and are interacting with the territory and mixed fleets. So we looked at what happens when we have city center restrictions. So what happens when we, for example, forbid entering the city center for some vehicles, or when we forbid or when we give it, when we require to pay for it. So when we add a price tag on entering the city center. So the question was, so actually what we see with logistics fleets, that traffic volumes cannot be just shifted to public transport or to bicycles or to walking or to other modes, but still there need to be some trucks or some vehicles to enter the city center to deliver goods. Fleet managers, they need to optimize their fleet operations for a given restriction scheme. So here you see, for example, one example where the vehicles in blue are entering the city center. So these are the electric vehicles, and most of the combustion engine vehicles will be staying outside. But now the question we asked ourselves was the impact of different pricing schemes, and we looked at 3 different cities, so Paris, Vienna, and New York. And we looked at per entry fees, total prohibitions, and per distance fees. And in this example, you see, for example, for one specific vehicle, the difference when we have an unrestricted case or a fee. And so in the unrestricted case, the combustion engine vehicle will traverse the city, and in the restricted case, it will stay outside of the city and only visit the customers where it really enter the city where it's really required. So this has a clearly effect on single tours. But when we look then at the fleet composition, what did we see? That actually the fleet composition stays quite stable even with increasing fee, but that there is a certain fee threshold, a break-even point, where it makes sense to switch from internal combustion engine vehicles to electric vehicles. So at some point, when the entry fee gets higher than 10 euros per entry, or when the distance fee gets higher than 30 cents per kilometers, then suddenly the fleet composition switches, and we see the need for, or that it's more beneficial to use electric vehicles in the city center. And what we see as well here on the right-hand side is that as soon as we use electric vehicles, also customers outside the city center are served by these electric vehicles, which is what is actually good, right? Because as the vehicles are there, they are used, and they are also used more than only in the city center, which is from the local pollution point good news. So that's the conclusion of the second research we did, case study, that was somehow the continuation of the first one, where we see that fee-based restriction can enforce the same solution as a complete ban of internal combustion engine vehicles from city centers. Event-based fees policies are more robust than volume-based policies. And as I said, besides reducing local emissions in the city centers, this access restriction can also help to reduce greenhouse gas emission in general, of course, if the energy comes from non-greenhouse gas emission electricity production. And what we saw also, because we looked at different sizes of city centers, that this greatly impact the effectiveness of restriction policies. If the city center is very small, or the limited zone is very small, then it will not have a great impact. But if it's large, there's lots of customers in there. So here we looked for the larger one at whatever is inside the peripheric, then it has a great impact. That was the second part on the freight vehicles. And in some other work with another PhD student, I looked at shared autonomous electric vehicles. So we did a case study here on several topics, but here I present one part of it that was on specific charging station location placement, where we looked at Rouen. And we did a simulation of, so agent-based simulation of the Rouen area. So we introduced shared autonomous electric vehicles, so we call them robo-taxi, into the city area of Rouen, so greater Rouen area, where we had a big number of vehicles we introduced there with a certain price. They were specific Renault Zoe vehicles that allowed ride sharing, but we did not do any rebalancing in this part of the study. And we looked at different models of how to place charging station depending on the demand for these vehicles. So we first did a simulation without taking into account recharging. That gave us the real demand part. And then we did the simulation again with the recharging part, with the given demand. So in order to know where to place the recharging stations. And what we saw in this study, and we also compared different modes of recharging. So standard recharging, quick recharging, or fast charging, and also actually battery swap, that might become interesting again in the case of homogeneous fleets, right? Because there you have much more leverage on things, and you have only very few vehicle types, and there it can make sense in terms of economy. So we looked also at this battery exchange, and what we saw that the performance of these shared autonomous electric vehicle systems or fleets is strongly correlated with the charging infrastructure, especially after peak hour. Vehicles have to come to recharge. So, for example, increasing the number of charging units per charging station will have an impact, because vehicles have been queuing actually in front of chargers in our simulation models, or deploying rapid charging will also increase system performance. And when we introduce battery swapping, where we assume, for example, 5 minutes for the battery swapping operation, then we obtain a much better performance. And performance means that we can reduce waiting times for the passengers, and we increase also the kilometers of the fleet where a passenger is in the vehicle. So this, in such systems, when they will be deployed in large numbers, charging stations and how to charge the vehicles is really of great importance. And this shows, as the topic of this webinar is I would say the interaction between territory and mobility is huge, and the charging infrastructure that is deployed on this territory. So that was it for the 3 projects I wanted to show you. And now I want to give you some research perspectives. So what we'll be doing in the next month. So we will be looking at different approaches, exact approaches, heuristics, also reinforcement learning for the dispatching and repositioning of robotaxis. So that's one part. And then there is another part where we are investigating the interaction of these robotaxis fleets with the power grid. So we are interested also in resilience. So how can these vehicles help to make the grid more resilient, and how they are interacting, and how they can improve the overall system efficiency. So thank you for listening, and please feel free to ask any question. You can get more information on the chair at the website of the chair. You can follow us on Twitter, or myself on Twitter as well. Thanks.
Thank you very much, Jakob. Very, very interesting results of your projects. So please go ahead with questions. Thanks again, Jakob. Now I'm inviting Panayotis Andreanisis to the floor. Panayotis, are you there? So just a few words about Panayotis. He's a graduate from the Hellenic Army Academy, and he's also holding a Bachelor of Science degree in economics from the National and Capodocian University of Athens, and a diploma degree in electrical and computer engineering from the National Technical University of Athens in Greece. He received his master's degree in production management and his PhD degree in the area of design and analysis of electricity market mechanisms from the University of Thessaly in Greece as well. And he was a postdoctoral associate in the Division of Systems Engineering at Boston University. Panayotis, the floor is yours. Very happy to have you among us. So please go ahead.
Thank you, Amira. Thank you for the invitation. The question that we are addressing in this presentation is how to optimally schedule distributed energy resources in general, which include, of course, electric vehicles, but also distributed generation, say, for example, rooftop solar and smart buildings, etc. Now, you know that distributed energy resources, they pose significant challenges to the distribution grid, which means they create issues with voltage. We now may have coincident demand, but they also include many opportunities, and these opportunities are mainly related to the capabilities of their inverters. Say, for example, in this simple example of a rooftop solar, a smart inverter, which can adjust its power factor and decide how much of real power to produce and how much of reactive power to produce or consume. As you know, in distribution networks, reactive power is very significant. It is mainly related to voltage support, and currently this capability is not harvested. Moving now to electric vehicles, scheduling an electric vehicle which travels, say, from work to home, and these may be different networks. The question that we need to answer is how much to charge, but when and also where. And how about reactive power, which mainly relates to the inverter of the vehicle or the charger. Now, this is a simple example when we have one vehicle traveling. But how about this case, where we have multiple vehicles which travel and couple several distribution networks? And these networks may even belong to different utilities. Now, of course, we see that this poses a significant challenge in terms of optimization. So we have a very large-scale optimization problem, which we will see how to tackle. We will propose a method to be able to solve efficiently this huge problem. Now, before proceeding, just in brief to introduce a physical model which defines the power flows in a distribution network. I have a lot of equations in the slides, but we do not need to focus on the equation. I'll just present the ideas and have some references where you can follow up. Now, the power flows in a distribution network. So this is like a distribution line defined by the flow from one end minus the losses along the line should equal the flow at the other end of the line. And we have equations that define the current and the voltage drop. This is an old model introduced about 30 years ago, but it's quite simple model which we use in optimization and formulate an optimal power flow problem. Optimal power flow it means that we are optimizing the flows in the network to minimize the cost, but also we schedule distributed energy sources. So we schedule electric vehicles, we schedule the rooftop solar and any DRs that we have in the network. Something that is new in this optimal power flow problem, this optimization problem, is the cost of the degradation of the assets. And so I will focus on this model only on the degradation cost and a small and a technical issue which relates to a relaxation of the model to be able to make it convex and solvable. So let me say a few words on what do we mean by degradation of transformers, and what is the challenge that the electric vehicles are likely to pose in distribution networks in the very near future. So this is a pole top transformer, this barrel you see on the left, and this device, it is designed to be able to be overloaded for a small amount of time, say for a few hours. It usually contains oil, so the oil allows some overload, but then when it reaches a high temperature, the effect becomes an exponential loss of life. So, for example, if you operate this transformer at its rated capacity, then for 1 hour of operation, it will lose 1 hour of life. And if we do so, it is estimated that this device is going to last for about 20 years. Now, if we have, say, these 5 vehicles charging from the same transformer, then the transformer may reach even twice its rated capacity. And this means that for 1 hour of operation, it's going to lose about 400 hours of life. So it will degrade much, much faster. And if you think that this is very down in the future, I have included two photos from my apartment in Boston about 2.5 years ago. These are taken with a difference of 6 months, and you can see 2 Teslas charging on the left, and then these 2 Teslas have become 4 Teslas charging from the same transformer. Now, we have a physical model which explains this degradation and some interesting intertemporal effects of the oil, and long story short, we managed to model the degradation using a linear model. So that is one issue, and the next issue is related to a relaxation of this branch flow model, of the optimal power flow model, of a certain equality constraint, which is relaxed to an inequality constraint. And the problem with this relaxation is that we see that sometimes it is not exact. When it is not exact, this means that we get results for power flows which are meaningless. So another contribution is to be able to retrieve feasible solutions. So the way that we are doing it here is we are writing this inequality as a difference of 2 convex functions, and linearize one part and penalize the difference, and being able through a sequential algorithm to retrieve a feasible solution. I will not insist on the technical details and move to the idea of the decomposition approach that we are proposing. Now, writing a more abstract notation of the optimization problem, we can see that we have network variables and DR variables. So the red are the network variables. Say, for example, we minimize the network cost, and the blue are the DR variables, and we are minimizing the DR cost as well. Subject to constraints that couple the network and DR variables, and these are the power balance constraints. And we have constraints that only affect network variables and constraints that only affect DR variables. So we see that the problematic constraint is this. It's the power balance constraint. And there are, of course, many methods to handle such formulations. But we are proposing a method that we think it fits well the model and the use case of distribution networks. And the key idea of what we call a hierarchical decomposition is the following. Suppose that we solve the network problem by fixing the contribution of distributed energy resources. Say, for example, that we have the schedules of the vehicles, we have the schedules of rooftop solar, and we solve a network problem where we are minimizing the network cost with fixed contributions of DRs. Then we obtain these lambdas. These lambdas are dual variables of the power balance constraints. These are interpreted as the marginal costs, the distribution location, marginal costs in the distribution network. And we can think of them as tentative prices at a certain location and a certain time period. And we announce these prices to the distribution, to the electric vehicles, say, for example. And the vehicles, they minimize their cost subject to all their constraints and preferences. Now, this may sound familiar with other methods such as dual decomposition or ADMM, alternative direction method of multipliers, but we show that it's different, and the difference is When we add the regularization terms, the difference is that we obtain the dual variables from this network problem. And these dual variables, they are interpreted as gradients or subgradients of a primal function. So basically, technically, we can show that this algorithm falls into the class of proximal algorithms and enjoys convergence properties of proximal algorithms. How is it different from dual decomposition? The difference is basically in updating the duals. The difference, you see on the left, the hierarchical decomposition. So this is the network problem. We solve the network problem for fixed injections of DERs. We obtain the prices as the duals of the power balance constraints. And then we update the schedules of the electric vehicles, solving a cost minimization problem with some small regularization terms. Dual decomposition, on the other hand, updates the duals based on the primal imbalance. And I will move, because we are a little bit short on time, to a pilot study and show some results and then an idea for a practical implementation of this hierarchical decomposition. Now we have data from an actual distribution feeder which is located in Holyoke, a municipal. It's located in Holyoke, Massachusetts. And it contains a little bit over than 300 nodes and about 110 transformers. We have several scenarios which include electric vehicles allocated to the transformers, different patterns of electric vehicles, over 600 electric vehicles. Scenario with rooftop solar, of each of 10 kVA allocated to the two 10 kVA solar PV allocated to each transformer, a combined electric vehicle and rooftop solar scenario, and a high EV penetration scenario, which is basically double the base case EV. We initialize the algorithm by assuming that electric vehicles, they start with a schedule where they optimize against a time of use profile, which is basically the LMP, the marginal price at the substation or the transmission network, and they do not provide any reactive power. And here we show the projects on the convergence of the algorithm for the different cases, and basically what we see is that the algorithm converges to a few tens of iterations. This is a profile of how we derive the optimal contribution of reactive power, and we see that we start initially from a non-optimal profile, which is the black line on the top. And gradually, as the algorithm proceeds, we reach the optimal profile, which is at the bottom, in practically a few of iterations. And by optimally, we mean the amount of reactive power that should be provided by the electric vehicles and DRs in general. Here are the electric vehicles only, to minimize the cost of the system. In the combined electric vehicle and PV scenario, we see here what is the spare inverter capacity. In other words, we see that the optimal allocation does not fully utilize the inverter of the resources. And last but not least, we see what happens in the increased EV penetration, and here we show the marginal costs for real and for reactive power. And what we see is that The yellow line, which has a spike, includes, it refers to the first iteration, so it refers to non-optimal schedules. And the dotted blue line, which refers to the real power marginal cost, refers to the optimal schedules. We see that when the schedules are optimal, so at the end, when the algorithm converges, the marginal costs are smooth. And this is an interesting finding, because typically we expect that nodal or locational marginal cost should be like highly volatile, and this is considered as a negative as a disadvantage of locational marginal cost. However, at an equilibrium, when we optimally schedule, we see that optimally scheduling results in much smoother profiles. And what explains this much smoother profile is basically the cost of the degradation. The degradation is presented at the lower figure. The red loss of life, it includes the amount of hours that are lost per hour of operation, and you see that the red pattern is high degradation when we start with non-optimal profile. So this means the transformer is overloaded, and the degradation much smoother. These are the blue bars when we have optimal schedules. Now, finally, I'll just show a slide on how we could potentially implement in the future this scheduling of DERs. So the idea is a platform that will receive network information and also information of DERs. Say, for example, an app that will provide where the user can provide the preferences, where the traveling preferences, and for the next day. And this platform will optimize the networks for fixed DR injections. It will provide prices or price signals to DRs, which will self-dispatch, respond, and iterate until we discover the marginal cost, and eventually we get the prices right in distribution networks. So this concludes my presentation. Thank you for your attendance, and happy to take any questions at the question chat.
Thank you very much. Thank you very much, Panagiotis.
Technical.
PV, it's photovoltaic. It's a solar panel.
Yes.
Okay, so thank you. If you have any questions for Panagiotis, please do it. Write it down. We will discuss later. And now I want to welcome Olivier Juin from EDF. So some few words about Olivier. He got his PhD degree in computer science and mathematics at l'École nationale des ponts et chaussées. He joined EDF R&D in 2018 in the Osiris department, where he worked for 10 years now on optimization methods and software development for the day-ahead optimization production schedule of EDF power plants. Now he recently joined the team working on electric mobility and supporting electric vehicle subsidiary growth. So welcome, Olivier. The floor is yours. We're very happy to have you also, to have representatives of EDF.
Thank you very much for the invitation. So my talk today will be about how you can use electric vehicle flexibility for the electric system. On the previous talk, we saw that it can be a huge stress for the transportation network or the distribution network, but it can also be a huge stress for the producer. And so today we will see how we can mix together EV flexibility and electric system with the FCR case. So FCR stands for Frequency Containment Reserve. I will present that in a few slides if you're not used to this kind of services. So the outline of the talk will be this one. I will first go for the context and the objective of this work, then the mathematical formulation, and then I will present some result and perspective, very few because I cannot show all the result we have. And finally, I will also present some work we are doing with some subsidiaries of EDF. So the context and the objective, I told you that the EV charging can be can generate a huge stress for the electric system, and so we'll see some of this in the few slides. So if we look at some facts for the French transportation, we can say that 30% of the total energy is consumed by the transportation in France. So it's a huge part of our global energy consumption. And almost 98% of this energy is from gas. So petroleum or biogas, but it comes from gas. And road transportation represents 90% of it. So basically, if we switch all the EVs or trucks that are driving today from gas to electric vehicle, then we'll translate a lot of energy consumption from gas to electricity, and it will generate a lot of stress. We saw that for the distribution network, but also for the transportation network and for the producer, in a sense where, well, the distribution network wasn't built for this kind of consumption. Neither the transportation network plus the electric producer. If everyone is consuming energy at the same time, then it will generate a huge peak. If everyone charges a car when you get back home, then it will generate a huge peak of production, and the production system is not built also to stand up this stress. So basically, if we look also at how much electric vehicle will well, how we think that people will buy electric vehicle in Europe, China, and all other countries, we see that it's quite exponential today. And so basically, we have to make sure that we anticipate all those new EVs in the system. And one way is to improve the network, improve the production plant, but also to improve the way we charge our EVs. So basically, this is smart charging. But there is different kind of smart charging. So, well, the way we do smart charging is to improve the way we integrate the charging schedule with the grid, the electric grid, but also the electric production. And the first level is smart charging, where we can shift in time the charging schedule such that we won't consume electricity everyone in the same time, and so we will avoid consuming electricity at the peak demand. But there is another way we can improve it, is using something that is called vehicle to grid. I don't know if you know about it, but it's called V2G for short. And this technology allows the electric vehicle to discharge its power to the grid, to the power grid. And in that sense, it's a different kind of framework, in the sense where you can also reduce the global peak demand. On the first hand, if you do smart charging, you can just avoid charging during the peak demand. While with V2G, you can also decrease the stress on the peak demand by re-injecting power at the peak demand. So this graphical representation here shows you the three kind of strategy. If you have only plug and charge and you're forced to charge when you plugged in, if you have smart charging, then you can reduce the stress and charge slower, or you can charge at different time, such that you will have a less impact on the grid. But if you have V2G, then you can also re-inject power when it's a big demand. So basically, you can discharge your batteries and charge later on. And that's a way to integrate, to improve the integration with the electric system. And so in this work, we want to explore a tight integration of EV charging, or V2G charging, with the electric grid. And that's the case of FCR. Sorry, kids kids in home. And so frequency containment reserve is, what is this? Well, basically the electric grid, the frequency of the AC power in the electric grid is 50 hertz in Europe, 60 in US, and it's mandatory to keep it at 50, very close to 50 hertz. Well, for security reason within the production units, thermal or hydraulic, but the frequency also reflects the balance between consumption and production. So basically, when there is not enough production, the frequency will go low, and if there is too much production, then the frequency will go high. And every day, the producers keep some reserve, the power reserve, to dynamically adjust the production to maintain the frequency very stable around 50 hertz. And so this power reserve is called the frequency containment reserve, because it's used to make sure that we don't go too high or too low within the frequency. And so in this work, we develop a method to optimize the smart charging for V2G EV fleet, in order to dynamically adjust the charging power according to the frequency, while taking into account TSO requirement for the FCR services. And so this is basically the latest and also the tightest integration with the electric system, because this maintains the basic, the very basic security services for the electric grid. So the mathematical model for now. We develop a mathematical model. I present here a very simplified version of the one we developed, but it keeps the most important part, and we'll see how it is modeled here. So there is some assumption also that I'm making for the presentation, is that we assume that the FCR capacity, so the power reserve that we want to keep, is already defined. So we know, for example, that between 8 and 10, we want to keep 20 kilowatt for the to participate to FCR, or 100 or 200 or 1000 kilowatt. And so we also know the time of arrival and time of departure of EV within the fleet, and also the state of charge at the time of arrival for every EV. So all those data, well, those assumptions are here for the model, but we also, well, there is a way to get all those data in advance. Anyway. So the problem is to construct also a charging schedule that will anticipate the arrival and departure and the charging, but also this need of power reserve to keep it and to dispatch it in real time for the according to the deviation of the frequency. But we also want all EVs to be fully charged at the end of the charging station, such that the user, the quality of service for the user will be optimal. But we also want to make sure that we preserve enough power and energy capacity for the FCR service in order to maintain also the quality of service for the TSO. So some notation. Well, basically, we have the charging power PEV. If it's positive, it means charging, and if it's negative, it means discharging. The battery, the state of charge of the battery, the capacity, which is the maximum capacity for the EV, the electric cost, also to charge at the best time in terms of electricity cost. We integrate also some battery efficiency, and also the power FCR EV of T, which is the power reserve for the FCR service done by this EV, such that the overall sum will be equal to the demand in the FCR demand. and also the time of arrival and the time of departure for every car. So the model is very simple and very basic here, because I simplify it for the presentation. So we want to minimize the overall charging cost, which is the sum of CTPV, and subject to the flow or the charging equation, basically. So the battery, the energy within the battery results of the previous state of charge plus the energy that we want to put inside the battery or we want to remove from the battery. And the battery capacity, well, we won't be able to overcome the battery capacity for each EV. And the power also has to be within the limit of minus Pmax plus Pmax, which is the maximum power for the charger for this EV. Can depend on the EV basically, but I remove this dependency. And also the state of charge at time of arrival, the state of charge at the end of the charging session, and the fact that we cannot charge when the EV is unplugged. Now, if we move to, so this is basically a very basic V2G smart charging optimization problem that we can solve with any kind of approach like linear programming. But we will improve it, or we will enhance it with the FCR requirement. So basically, when you enhance it with the FCR, you have to add a few constraints and a few variables. So basically, we have to insert a new variable for FCR participation for this for each EV, which is positive. And now we have to make sure that even if the FCR activation, we have to activate this power in real time. We have to make sure that we do not overload the system in terms of Pmax, but also in terms of capacity for the battery. So basically, we have all those 4 constraints here to make sure that if the frequency go high or low, then the power, the overall power won't go higher than Pmax or lower than minus Pmax. And the same for the battery. So basically, we have to take into account into our reserve, the power reserve, but also the energy reserve within the battery. And then we have to satisfy the demand also, such that the sum of all the FCR participation for all the EV is equal to the demand. So basically what we have sold to the TSO for tomorrow. So the basic idea of this algorithm is very simple. So we will build a charging schedule, which is in blue here, which is the blue arrows, going from the initial sock to the final sock, which is 100% of the sock, the capacity. And in the same time, we will have this cone of power that we can do, basically minus Pmax plus Pmax, which result in a cone of energy within the battery. And we'll have to make sure that well, we can go lower than 0 for the battery and higher than capacity max for the battery. So basically, we reduce the available feasible cone to a shorter one, and then we'll have to also reduce it to make sure that we will reach the final sock, the final energy within the battery at the end of the charging session, but also to make sure that the overall sum of all those cones will be equal to the FCR demand. So basically, those cones represent the reserve in energy that will provide for the TSO to do the FCR services. So for all those time steps, we'll generate those energy reserve, and we'll make sure that those energy reserves are feasible to the system. So if we look at some results and perspective, we can see here the overall power for the fleet in yellow, which is the power we should have been, without the FCR participation, so the overall fleet power. In green, you see when the FCR activation is done. So basically, there is some timestamp here where the fleet do not participate to FCR, and then the green and yellow are well, the green is equal to the yellow, but on some timestamps here between 8 in the evening and 4 in the morning, you can see that the green is reacting to the FCR, and we are deviating from our announced overall power. So basically, we are going from the blue arrows to something that is higher or lower, reacting to the frequency of the service. Of the grid. Here you can see also the capacity in below it. So we simulate 100 kilowatt of capacity between 8 in the evening and 4 in the morning, and 0 everywhere else. Here you can see the charging power, the state of charge, and the power in green. So the state of charge is in yellow, and orange is the maximum SOC, and green maximum capacity. And in green, it's the power of the charging power. And you can see that during 8 and in the evening and 4 in the morning, there is this power that go up and down and reacting to the frequency. So if we conclude, we were able to integrate them with the smart charging with SVR services, guaranteeing both quality of service for the user and the TSO. And now we are moving on to new services to integrate it fully with the electric system, almost like a virtual power plant. So all other ancillary services, basically. And well, I told you this system was a simplified one because basically this already exists and much more. And it's a subsidiary from EDF called DRIV, which is basically a smart charging technology for flexibility market. It aggregates EV flexibility, V1G and V2G. So regular smart charging and V2G smart charging. It does it in France, UK, Italy, Belgium, and Germany. And it has already some results. So basically, the basic idea here is that you can maybe earn money by providing your EV flexibility to the system, and DRIV is doing exactly that. Thank you for your attention, and I will be happy to answer the question.
Thank you, Olivier. Can I ask you to stay on the scene? And I want to ask Emilia, Jacob, Eva, Panayotis to join us if it is possible. We have a couple of questions that are there in the chat room. So please come. Maybe I can see yes. Okay, I see you all. Still waiting for Panayotis, and he's here. So we have 10-15 minutes to discuss a little bit about what you have exposed, and we have some questions. I don't know, how do you want to proceed? We have a question for Olivier, for instance, about the standard. Do you see her?
Yes, I saw the question. Yes, we also consider ISO 15118. For now, we use OCPP for the communication, but for sure, in the future, we are basically working on the ISO also, and we have teams also helping to develop the standard for this communication.
Okay, thank you. I hope, Farah, it's good for you. You have also answered, asked, do you use any standard for EV charging for Emilia, I think? Do you want to give some points, Emilia?
So these charging standards, that's not something that's studied by the shared energy team at Vedecom. However, there are other teams at Vedecom that work on the communication aspects and also on the also on the normalization aspects. So there's some work on that, but I'm not an expert on that side.
Okay, thank you. Do we have other questions for Emilia? Help me if you want. If you, I'm scrolling the. Well, no more questions for Emilia. What we note is that we are going to a more distributed and disruptive way of using the vehicles and charging them. That was pointed out by Emilia for this hybrid way of doing things. Jakob put also the spot on that, and Panayotis, you spoke about the DARE, also the distributed energy resources. So what we remark is that it's initiating a new way of doing things, more unstructured, new business models, maybe. Do you have any thoughts about that? Because it's completely new to the energy management system.
I can go ahead. Yes, as you very accurately, as you said, it's going to be new business models that will arise from in this new era. And I think one of the use cases and the model will be platforms that will facilitate scheduling for the next day. And that's I think this is key in the future, to be able to schedule loads such as electric vehicles and adjust during the day. So what is the role of the distribution utility in this? Is the distribution utility going to be a player? Is it going to be a neutral entity? Also, how an issue that we think is not well captured yet, because there is no regulatory incentive, is what happens to the impact on the assets of the network. We have studies already from the 2010, like almost 10 years ago, that show that high penetration of electric vehicles are going to overload the transformers. This will require significant upgrades in the network. And the question will be, who is going to pay for that? Is it going to be allocated equally to the consumers, or is it going to be charged to those who impose on these negative externalities on the network? And so I think these will be questions that will be in the near future.
Thanks, Panayotis. Maybe Jakob or Emilia, do you have any new arguments on that?
I think so. From my side, I'm getting increasingly interested in this interaction, as Olivier presented, between vehicles and the grid. And I think especially what we will be working on in the future cities lab will be this part on uncertainty. So how to integrate uncertainty into all these models, because we have seen quite a few models based on deterministic views, but we are now starting to think what happens if we have data coming in, and what is happening when we don't have distributions for this data. So we are looking at distributionally robust approaches for taking into account uncertainty in this kind of vehicle-to-grid or interaction between the grid and the shared autonomous electric vehicles. So we are not looking at today's EVs, but we are looking at at fleets of shared autonomous electric vehicles that can be easier managed, of course, than electric vehicles of individuals.
Yeah, if I could just add, this is of course a very interesting question, the value of these different energy services and the new business models that are going to come from it. And also, of course, the questions of how we're going to share this value between the different actors in the system. So as I said, there's interesting work that was done by Andrew Thompson at Vedecom, who did a kind of a meta-analysis of the value of different energy services, so vehicle to grid and others. So I invite you to have a look at his paper. I think it was published in Energy Policy last year. And also a note on the uncertainties. I think that's a very interesting question as well. And I mentioned the work that's done by Dirk Lauinger at EPFL. And he has done very interesting calculations exactly by, well, taking into account the uncertainty in the presence of EVs and also in the size of the grid incident. And there's also a working paper on that. So if you're interested in that topic, you can have a look at his work as well.
Yes, please. Can you share it? Okay. Well, the subject is too complex to discuss all the elements and the dimensions here. We have a couple of questions to Olivier, to Eva, but Eva left us, and I think she has written her answers to you. Emilia, you asked about where are the stations deployed, and what is the pricing, I think. Yes. Okay, Olivier, you had also from Olivier Lambert a question, and you answered. Okay, great. Do you have any comments to add, or what was your main constraints, barriers to doing your research? Is it the availability of data, the lack of transparency of the model and the policy makers? Maybe, I don't know. If you want to share your experience.
Yes, sure. Getting reliable data is quite difficult. Plus, all the assumption, getting the state of charge beforehand is also very difficult. Currently, without the ISO 15180, it's very difficult to get the state of charge of a standard AC charger. So if you have a DC charger, then it's very easy. You can use the OCPP to get the state of charge. But if it's an AC charger, getting the state of charge is very difficult. And so basically having all the data to have a fully aware model of the state of your system or your fleet is very difficult. So sometimes it may be better to have some kind of model that is working with unknown data. So the state of charge basically is very difficult to get, and also you can try to predict it, but it will be likely that you're making mistakes there. So having data is very difficult, basically, even when you work with people that have access to raw data. And even when you get data, sometimes there is a error of measurement here, and also the charger are not always working as you expect it. So basically, you request 10 kilowatt and you don't get 10 kilowatt, and so all those small details details to make it difficult to go from a mathematical model to a real life problem. So you have to cope with that within your mathematical model, and that's some details that you don't share easily with the people.
Yes, from theory to practice.
Yeah, basically.
Okay. If we don't have any new comments, or I thank you very much for the quality of your presentation, for your mind openness to share with us your latest research. One question was about the sharing or not of the slides. If you want to share them at the end of the event, please let us know. You can continue asking questions and answering in the slot. So we'll have a small break, and then we'll get back at 10:55. I think, yes, Olivier, you have a lot of questions to answer. Thank you again. And I just to remind that the second session will be led by Rim Kada, which is my colleague and the leader of the optimization team. So talk to you and see you in about 5 minutes, 10:55. Thank you again.
Thank you.
Thank you.
Thank you.
Hello, everybody. I am Rim Kada. I'm a researcher at IRT Systemics and team manager of scientific computing and optimization team. I'll be in charge of animating the second part of the webinar, which in the first part we saw fleet management, having a given charging infrastructure. In this part of the seminar, we will be focused on what is on presentation that will tackle the best way of deciding where to put this charging infrastructure and how to manage it. So for this, I'm happy to welcome our first speaker for this part, Marc-Olivier Mété. Marc-Olivier got a master's degree in electrical engineering from Centrale Supélec in 2019 and a master's degree in economics from Université Paris-Dauphine that same year. He started a PhD on optimization of electric vehicle charging infrastructure in October 2019 at the Laboratoire de Génie Industriel of Centrale Supélec and the Institut VDECOM. Marc-Olivier, the floor is yours.
Okay, thank you, Kim. Thank you everyone for being here, and thank you to Systemics also for organizing this seminar. So for my part, I will present the modeling options and perspective for planning electric vehicle charging infrastructures, which is a work that I did at the Institut VDECOM, which Emilia presented you just before, and the LGE at Centrale Supélec. So this presentation will be quite general and will take again some elements from previous speakers. So first, I will set the context and quickly introduce a simplified electric vehicle charging infrastructure framework. Then I will present the challenges related to the infrastructure and the different methods of deploying charging stations before concluding. So let's begin with a bit of background on electric vehicles and charging infrastructure. Here I will be, there is no animation. Wait, that's not problem. So here I will be quite brief. We all know that it is necessary to reduce our greenhouse gases emission, and that the transport sector emits a good part of them, in addition to other nuisances such as, for example, noise pollution. So to reduce those transport-related nuisance, we have found an alternative, which are electric vehicles. And electric vehicles have a very low local environmental impact and lower overall one than internal combustion engine vehicles. But despite of these advantages, for the moment, there are two main points that hinder the democratization of electric vehicles. The first one is the price, and the second one is the range anxiety. As you can see in the slide, the price is supposed to no longer be a problem, mainly because in 2025, the price of a new electric car is expected to be the same as that of the Camel 1 of equivalent class. So it's supposed not to be longer a problem. But the second problem is the range anxiety. And the range anxiety is basically the fear for users that they will not be able to complete their trip with an electric car without running out of battery. And that's really the main problem to take care of in order to allow a large democratization of electric vehicles, because if users fear that, if they fear to not be able to complete their trip, they will not change their conventional vehicle to an electric car, and we already said that it's a bit a shame for the planet. So let's leave the range anxiety for a little moment. We'll be back on it later. Just to quickly define a simplified framework for recharging infrastructure. So what do we have? First, we obviously have the electric vehicle users and the charging infrastructure that are in interaction. So the charging infrastructure provides power to electric vehicle users, and electric vehicle users need a charging infrastructure in order to be able to complete their trips. And the streets, this interaction takes place in the transportation network. And then we have also the power grid that provides power to the charging infrastructure, and it is important to take it into account because network constraints don't allow to do anything with charging infrastructure. For example, there may be some restriction on the power that can be installed at certain locations. And finally, and that is one of the great advantages of the electric vehicles compared to the thermal vehicle, electric vehicles users can have the possibility of charging at home. So that's a very big advantage for electric vehicles. And so this ecosystem brings many parameters to consider when deploying a charging infrastructure. So in particular, the center of this ecosystem lies in the point of triptych charging infrastructure, electric vehicle users, and transportation network. And on the one hand, you have a charging station, which can have, for example, different cores, different capacities. In the other hand, you also have the roads with different type of road, can be highways, city streets that have different amount of vehicle flow, different traffics. And finally, you also have, of course, the electric vehicle users who will not all have the same needs, the same behavior, the same battery capacities, the same vehicles. So this simplified framework just bring a lot of parameters to the question how to deploy a charging infrastructure, and it showed that answering this question is not so easy. So I'm sorry if the slide is a bit messy. It should be some animation, but it doesn't work. I don't know why. So now we have a bit of background. Just let's switch to the issues linked to the charging infrastructure. So as we saw a couple of minutes ago, the main challenge to get electric vehicles accepted by consumers is to solve the problem of the range anxiety. And we can ask what is hidden behind the range anxiety. So first, it's a fact that except for rare luxurious models such as the Tesla or Roadster, I think, electric vehicles have a really lower range than internal combustion engine vehicles. So we can increase this range by increasing the electric vehicle's battery capacity, but in that case, first you increase the price, so the price becomes a problem again for the large adoption of electric vehicle. And second, this does not really solve the two other following points, because there is also the problem of the refueling time. All of you have already filled up a vehicle with gas. It only takes a couple of minutes, and then you can drive for hundreds of kilometers. But with electric vehicles, it's a bit longer. It can go from 30 minutes in the best case to 20 hours for a full charge. So it's a bit more complicated. And this charging time is if you can find a charging point, because while you can find gas station almost everywhere, it is far more complicated to find an available charging point for electric vehicle. So in order to take out the 3 points, the solution is to improve the charging infrastructure in order to have one that is adapted to the user's need. So we can say, okay, cool, let's build a charging infrastructure and everyone will go electric. It sounds quite simple, but in fact, it's not really, it is not, because charging infrastructure, and that's an important point, costs a lot. And you cannot, you will never have somebody that will spend such an amount of money without having the certainty of a return on investment. So we need to have the electric vehicle first. But nobody will buy an electric vehicle if there is no possibility of charging it and using it as a normal vehicle. So we need to have the charging infrastructure first. So here there is a kind of chicken and egg problem, because electric vehicles and charging infrastructure form a two-sided market, and one cannot exist without the other. So what I've been found is that the first step must be done in the infrastructure side, but because of the related cost, this must be done in really a coordinated manner. And that's important. It must be done accompanying the increase in the share of electric vehicle in the vehicle fleet. You cannot put your infrastructure all at once and say, okay, now the electric vehicles will come. It's too costly. So you must to have a coherent agenda to avoid blocking the democratization of electric vehicles. Okay, so to plan the deployment of such an infrastructure, we have to consider that the charging infrastructure is at the junction of 3 domains. In addition to the user aspects with electric vehicle acceptance, we have 2 more research areas that are emerging in the deployment of recharging infrastructure. You have the technical one, what kind of charging station to put on for many vehicles. You also have the economic one, because you want to know what will be the investment cost, the return on investment. And then you have also the EV acceptance, the user acceptance of electric vehicles, which we spoke about just before. And at the intersection of technical and economic file is the electric grid, because as mentioned before, the power grid impose some constraints to charging about the charging the station and some locations. At some location that can lead to harmful economic impacts if not respected. And you also have the infrastructure cost, as faster charging stations are also more expensive. At the technical and electric vehicles acceptance area, we can find the charging time and the charging availability. We already talked about that before. And at the intersection of the economic and electric vehicle acceptance areas, there are the land coverage, because you don't want to have blank zone on your maps, and of course the charging cost for users who want to travel as cheaply as possible, while the charging infrastructure investors want the return on their investments. So that means a higher cost for users. So there is an equilibrium to find here. And those lead to three issues in the deployment of charging infrastructure that are the location one, where to put the charging station to have the best coverage. The sizing one, how many stations with how much power to put at the chosen locations. And you also have the using one. So who will use the station and what do they need? And the importance of those issues and the way to answer the related question depends on the goal given to the infrastructure deployment. So basically you can group those goals into two categories. So the first one is the deployment which aims to minimize the installation cost for a given demand. And the second one is the deployments which aims to maximize the service offered to users for a given budget. So to minimize the installation costs, the criteria to optimize are generally the different cost or source of return on investments, while maximizing the service focuses on optimizing the constraint of using the charging infrastructure. So now that we know why we want to put a charging station, let's focus on how we can do it. So there are only three ways of approaching the problem. The first approach is the node-based one. So in this case, you take the problem as a coverage problem. How does it work? You have in the network a set of potential locations and a set of demand points represented in red in the figure, and you want to cover the demand point under consideration of cost. So basically, when you put a station, it can cover a certain area, and you put station in order to cover the demand points. So here we have three main node-based categories that have been identified. Jacob already told that before. That are the set covering location model, which aims to minimize the number of facility while covering all the demand. The maximum coverage location model, which aims to cover a maximum of points under a cost constraint, and the P-median, which aims to minimize the distance between the demand and the charging stations. The second approach that has been identified is the path-based approach. So here you take the problem as a flow capturing model. You have a set of potential location again, and this time you want the measurement of the vehicle flows at the locations. That is represented in this diagram by the thickness of the lines. And the objective is here to capture the maximum amount of vehicle flow. So when you put the station, it covers a flow pathing at the station, and what you want is to cover the biggest flows. So here we have two main path-based categories, which has a flow capturing location model, which aims to maximize the amount of vehicles passing in front of the stations. And you also have the flow refueling location model that takes into account the limited range of the vehicles. And the third approach that has been identified is called the tour-based or the activity-based approach. So here we see the location problem as an event capture problem. So as the two previous methods, you still have a set of potential locations to put your stations, but this time you need the vehicle's activity individual data. So for example, where each vehicle starts, where it stops, for many time, etc. The amount of data required just depends on what you want to consider in the model. And the goal at the end is to locate charging stations where there are load opportunities. So here in our little example, we suppose that there are three people daily traveling on this network, so the blue, the green, and the red one. And to make it simple, we suppose that they may stop at each node that travel through. and we try to capture the top events. So basically, we can see here that there are 3 vehicles charging at the charging station at the right. So stopping at the charging station at the right. So here it's the best place to put a charging station. And then if you have the budget to a second station, you can put a second station, such as, for example, the one in the middle, because 2 people are stopping at this place. So that's one of the best places to put a second station. And this principle is quite simple in theory. It's quite simple to visualize, but as I said before, you can take into account a lot of parameters, such as the average parking time at each place, for example, because if everybody goes to a place but only stay 5 minutes, there is no point to put a charging station on it. So you can also take into account the state of charge of the vehicle, because if people come to a station fully charged, there is also no interest to put a station here too. So you can take anything you want into account, as long as you have the required data, because such data, for obvious privacy issue, is not so easy to collect. So that's why a multi-agent simulation model could help in order to develop those kind of models. So to sum up those 3 approaches, on urban territory, the node and shore-based approach are better than path-based one, because in city you usually make short trips and you don't want to make a stop just in order to refuel your vehicle. So charging opportunities are when vehicles are parked. So both node and shore-based approach are adapted to have infrastructure that meets this demand. But on highways, the path-based is better, because here you don't have really different behavior than with conventional vehicles, and there is less interest to use the shore-based method that is more complicated to implement. And to finish, the shore-based approach really takes into account the user behavior. So as I said before, it aims to capture charging opportunities from the user's behavior, while the two users just try to estimate the power demand and meet it. And this makes, in my opinion, the shore-based method the one which should lead to the infrastructure that would best suit the users, and so make the spread of electric vehicles easier. So to quickly conclude, what is to be remembered is that electric vehicles and charging infrastructure form a two-sided market and have to develop at the same time, with the first step that have to be made from the infrastructure side in order to set in motion the democratization of electric vehicles. That 3 main locations have been found in the literature, and the tool-based one seems to be the best method to guide coordinated large-scale infrastructure developments. And to finish, the charging infrastructure deployment cannot be done all at once and must be over a period of time. And as soon as there are more and more charging stations today, the deployment must take into account the previous existing charging infrastructure. So there is a need for a coherent time schedule in the deployment in order to have the most appropriate infrastructure at each step of its development. I think I've been a bit long. Thank you for your attention. And if you have a question, I'm happy to answer it.
Thank you, Marc-Olivier, for your insightful presentation on the different modeling choices. The next talk will be given by Aboud Mourad, and will tackle analyzing fast charging potential for electric vehicle with local photovoltaic power production in French suburban highway networks. So Aboud is a previous PhD candidate at IRT Systemics and Centrale Supélec, mainly specialized in developing optimization models for electric and shared mobility applications. Currently, he is a research and development project leader at Explayer Group, working on the validation of the connected mobility systems. Welcome, Aboud. The floor is yours for 15 minutes.
Hi, everyone. Thank you, Reem, for the introduction. So I suppose that you hear me well now. Okay, so today I will be presenting to you our recent research on the deployment of fast chargers for electric vehicles through a case study on a suburban highway area, which is in our case will be Paris-Saclay. So this research was conducted last year with some colleagues at Centrale Supélec and at IRT Systemics, and in collaboration with Paris-Saclay agglomeration. So if we are ready, let's start. So first, in order to introduce the subject a bit, so here we consider, in our case, a hybrid area in which we have different residential and industrial zones. So it's Paris-Saclay, which means that we might have passengers that are traveling through the area, going to their work in the morning and returning back in the evening. Or we could also have some heavy trucks carrying products to nearby locations through a network of highways, as we have, for example, Rungis and the airport of Orly, just next to the area. So we might have a very mixed mobility patterns here in this area. In addition, here we have an electric grid, but we will also have a local photovoltaic center that will be supplying power to the distribution network in the coming years. So if we assume that many of these trips, people or good trips, will be performed by electric vehicles in the area in the near future, then the aim of our research was to see how we can deploy fast charging stations through the highway network for charging electric vehicles and trucks in very short times. So, however, this deployment must take into account passenger mobility flows, the available capacity of electric grid, and the possibility of integrating the locally produced photovoltaic power in order to supply this charging network. So talking about electric vehicles and their charging technologies, then chargers for electric vehicles can be classified into three main levels. So according to their power and charging time. So level 1 mainly for domestic charging, level 2 mainly for public and commercial charging, and level 3 is the one used for fast charging, especially on highways where electric vehicles need to be recharged at very short times. So if we take, for example, the Tesla supercharger, it can charge a vehicle in approximately 30 minutes. So it's quite fast charging technology. Now, in our operational problem, so it's important here to mention that here we treat the operational problem behind this deployment. So in our problem, we have a set of mobility paths representing the flows on major highways in the area. These paths are associated with a charging demand for both personal vehicles and heavy trucks. These demands are represented by the number of vehicles, electric vehicles that need to be recharged through the highway, and the set of locations that can be used as charging stations for electric vehicles. So these potential locations have some installation and land costs for sure, and are identified by the available electric capacity provided by the electric grid and some space limitations, because sometimes we are obliged to respect some space limitations. We cannot put as many chargers as we want. So as their charging time and capacities are very different, here we consider in this research two types of chargers. One for small vehicles, meaning personal vehicles, and the other for trucks, which require higher electric capacity in order to charge them. And by solving this problem, the aim is to select the appropriate locations for installing electric vehicle charging stations, while giving the exact number of chargers to be installed for each type at each station. So this is the main goal of our research. But for sure, we have to keep in mind that this deployment must respect the capacity of the electric grid as well as the number of parking places available at each location. Now, in order to solve this problem, we provided a data-driven approach that consists of three main stages. So first, we start by modeling the charging network and its demand. Then in the second stage, we model the photovoltaic power production within the considered area. And finally, we provide a optimization model in order to obtain the final deployment of fast chargers. And this is done for sure in parallel. This is done while analyzing the integration of locally produced solar power or photovoltaic power, as well as the potential enhancements that can be made to the charging network. So here we aimed really to see if we can give some hints or some suggestions on how we can enhance the actual electric grid in order to accommodate such increasing number of demand for electric charging. So in order to model this problem, as I already mentioned, we have a three-stage approach. In the first stage, we start by modeling the charging network and its associated demand. This was done by considering a highway network and taking the intersections of these major highways as our what we call coupling nodes. This is the points where the demand flow can change. And then these paths are built as a sequence of these nodes as defined by their actual flows, so the actual number of vehicles that are moving on these paths, and on the real traffic data for sure that we used in our research. So once these paths are defined, then we fix a set of potential charging locations by using first the actual charging locations, because here at Paris-Saclay there are actually some charging locations that are actually operational. So we use these locations, and we also use some service or gas stations that might be, in our opinion, among the first to adapt this new technology of charging, electric charging. So we use these two types of locations in order to define our potential set of locations for putting the charging, such fast chargers for electric vehicles. We then try to associate these charging locations to the defined paths so that our model in the next step could tell us which locations to use and how many chargers for each type we should locate at these locations in order to cover the charging demand. So that was the first stage. In the second stage, we model the photovoltaic power production. As I said, here at Paris-Saclay, there is a project of a very big center, a photovoltaic center. So the idea was to see how we can model this photovoltaic power production, which can help really in the future in supplying EV chargers. So as we all know, this photovoltaic production depends on different factors. Some of them are fixed, and thus can be known in advance, such as the irradiance on the surface of the solar power. But some of them at the same time are stochastic and thus cannot be determined in advance, such as the cloudness index. So the probability, if I can say, of having a fully sunny day is higher in summer than in winter, and thus the photovoltaic production would be higher. So to overcome this difficulty, this stochastic approach, stochastic aspect, so we have built a set of scenarios based on 4-day profiles. So here, as you can see, so it's fully sunny, partially cloudy, mostly cloudy, fully cloudy. And we have 8-day periods, because also this production could depend on the time hour. And we have also the 4 seasons. So in our case, the scenario is defined by a certain day profile, a day period, and a season, and is also associated with a probability. So here it's a probabilistic model. So based on real weather data that we obtained from the airport of Orly, which is just nearby, we could build our probability matrix representing the different scenarios and the amount of photovoltaic power that can be generated at each one of them. So once these two first steps are done, so the last step would be the optimization step. So in this step, we provide an optimization model. So here you just take a glance of the model. It's a wide model with many variables, so I couldn't have the opportunity to present it all. So this is just to give you an idea. So in this model, we have a set of variables that can tell us where to put our chargers and how many chargers to put at each location, where the aim is to maximize the covered demand while respecting some constraints, such as a general budget limit for the project, a minimum demand coverage, and some constraints related to the number of chargers that we can put at each location. That comes from space limitations, from electric capacity limitations, and some other constraints. So this is just to give you an idea. So here, once we have our model presented, so it's time maybe to get to the more interesting part, so to see our results of our case study. So let me start by a set of parameters or specifications. So we considered only 5% of the actual traffic flows at Paris-Saclay to be electric vehicles and trucks. So this percentage was fixed based on electric vehicles share market in France in 2020. So, however, this percentage can be seen as a starting point because we expect that this percentage is going to go up in the next few years. So this is just a starting point, and we were also interested in testing our model with higher rates of electric vehicles. Second, we assume that a fast charger for a vehicle operates at 50 kilowatts, and for a truck, it's at 250 kilowatts. So for sure, a truck needs a higher capacity for charging. And we finally assume that the charging of all vehicles and trucks to be homogeneous, meaning that we consider at each time we have a vehicle arriving to a charging station, then we assume that it needs to be fully recharged, which is not the real case, but this can be seen as the worst case. In the real world, what will happen is that we will have vehicles with 20–30% of charge, so it might be a bit better. But this is just to have our model operational and have some interesting results. So now for the obtained results of our case studies. So first, we have the complete distribution. We have obtained the complete distributions for EV charging stations at Paris-Saclay, as we can see here in the pictures. So numbers on the right is for the trucks and number on the left is for the vehicles. The solution indicates the selected locations, as you can see. So you can see that all the locations are on the highways that we have at the area, and the actual number of chargers to be installed. In general, we can see that we have up to 33% of the overall charging demand in the area which is covered by our solution. In the details, we can see that some paths are fully covered, some highways, while others are partially or poorly covered. This mainly can be explained by the few number of locations that are available or by the limited electric capacity at these paths. So our results could suggest adding some new charging locations at these paths where we need more locations, as well as increasing the electric capacity in order to accommodate more chargers. I hope I'm not running out of time. So some extra results. So here we try to increase the charging time, the charging power, sorry, of EV chargers with up to 4 times. And we can see that as we increase this charging capacity, our demand coverage rate can go up to 70% of the overall demand. But for sure, this is just theoretically correct, because at the same time we have to assure that the electric grid is capable of accommodating this increase. Otherwise, we will be increasing the capacity of each charger while reducing the number of chargers. So at the end, it won't change a big deal. So this is just to keep in mind. That was just to test and see how would this affect the coverage rate in case we increase the capacity of our chargers. Now, regarding the photovoltaic power production, which is also a very interesting aspect of our research. So if we compare the case in which we don't integrate this production to the network to other cases at different seasons, as we can see here in the table, where it is integrated, we observe that the overall covered charging demand can increase with 7 to 10% in spring and summer scenarios, which are the more optimistic scenarios when photovoltaic power production is maximal. So these results confirm the importance of such integration, especially at paths where charging demand is high and the capacity provided by the electric grid is limited. So the fact that this production is local. So as this center is locally located at Paris-Saclay, so this might be very practical and at low cost to integrate this energy to the grid in order to charge more electric vehicles. Now, the last element of our case study was to see things from a more business perspective. So we have studied 3 investment indices to evaluate the profitability, if I can say, of integrating photovoltaic power to the network. So these are the levelized cost of energy that represent the average net cost of electricity generation for the photovoltaic center over its lifetime. The second one is the return of investment, which evaluates the efficiency of an investment by measuring its amount of return. And finally, the payback period, which could give us the amount of time needed to recover the cost of an investment. So if we take 20 years lifetime, what usually you take in the literature, we can observe that the net cost of generating photovoltaic energy is estimated at 0.07 euros per kilowatt, which can be seen as the minimum cost of selling electricity at break-even prices, so that the project can be recovered during its lifetime. This cost for sure includes the charger cost and the extra expenses needed to operate and maintain this charging network. We can also observe that every 100 euro of investment in the considered photovoltaic center will be returned as 260 euros at the end of the lifetime. So we finally also can observe that this investment can pay itself back in approximately 7 years. So why these observations are important? It's just because it can give, especially for local authorities, it can give them some perspectives on how to evaluate the potential of integrating locally produced photovoltaic power into the charging network. My final slide, Reem, I'm sorry, I'm late. So regarding the perspectives, this research can be enhanced by either considering a full stochastic approach, because here we just considered a set of scenarios, we simplified the problem a bit. And the second thing would be to extend the analysis that we are doing by considering larger electric vehicle flows with additional photovoltaic centers that can enhance the charging service. And finally, here are some references for those who might be interested in more details on this research. So thank you for your attention. Please, if you have any questions.
Thank you, Aboud, for your very interesting presentation and case study. We'll get back to questions later on.
Okay.
Thank you. So now our last speaker is Benoît Soé. Benoît graduated from École Normale Supérieure de Cachan.
Again, I hear can you hear me? It's weird.
Yeah, there are some technical difficulties here. I was presenting Benoît while he can connect again. So Benoît is a graduate from ENS, Cachan, and he's done 2 master's degrees, one in clinical physics and one in applied mathematics at EDF R&D and Avignon University. His research is related to game theory and its application to the electrical and transportation systems. I hope, Benoît, your microphone issue would be okay.
Yeah, I hope so. Can you hear me?
The sound is a bit like the microphone sounds.
So you can't hear me?
Do you have earphones?
Yeah, I tried those at first, but they don't seem to work. That's a shame. What about now?
Did you change anything? We don't hear you anymore. Probably, if you can reduce the microphone volume with a bit of white noise, it might work. We don't hear you. You can change the settings of your microphone using the wheel on the bottom of the screen, and you should choose the right microphone output input. No. So probably without the earphones. Oh, we've lost Benoît.
Okay, can you hear me? You don't see, I don't hear anything.
If you can connect your microphone, it's not connected now. Yeah. Probably, Anne, you have a... No, we cannot hear. Yeah. It is still not functioning for the microphone. Can you check? I think, Benoit, if you can hear us, we can probably move to questions for the first two speakers while you set up your connection and try with another PC. So Aboud and Marc-Olivier, if you can come back to the screen for the Q&A session, please. So thank you very much for your presentations again. For now, we have one question from Flore to Marc-Olivier about which of the three approaches you presented, Marc-Olivier, is appropriate to integrate environmental impact assessment associated with the infrastructure. You answered. I don't know if you want to elaborate.
I already answered in the chat. I'm sorry, I didn't. I didn't see.
No problem. I don't know if you want to say more. You said okay.
I can say a bit more because as it is a written answer, it's a bit concise. But so yes, I said that it will probably be easier to integrate the environmental impact in the node-based approach, but I think in any case, the tool-based approach can maybe be a bit better than the others because it's really a user-centric method, so it ensures that the station will be really useful to users. And so on the overall impact of the whole infrastructure, maybe it will allow, for example, to have less stations than with another method, or to or maybe to develop more the electric vehicle fleet. And so it's not directly the impact of the charging station at the place, but the global impact that should be better with the tool-based approach. But it's really more complicated to integrate, I think.
Okay, and I have a kind of addition to this question based on the two approaches you presented. Can you say a bit about how you suggest time to be taken into account?
Taken into account. In fact, to be honest, I wanted to present that, but I did not have yet sufficient results to make a full presentation about it. So I stay on a more general topic. To integrate the time processes, I will be based on some forecast of. No, I will not be based on some forecast of the number of electric vehicles over time, but my idea is to see the impact of the infrastructure of the existing infrastructure in the adoption of electric vehicles. So that's a bit the contrary of the usual method, that is to say, okay, for example, in 2030, we will have this amount of vehicles, so we need this infrastructure. No, I want to try to do something like, okay, so I put this infrastructure and I'm going to see how many electric vehicles, it will bring to the global vehicle fleet. So that's a kind of incremental method over years with at each step an utility of having an electric vehicles, and depending on the utility, you have a certain probability to switch from internal combustion engine vehicle to electric vehicle.
Okay, nice, thank you. Aboud, I have a question for you. Yep. It's kind of a follow-up of a question Emilia asked during Eva's intervention about the placement of the candidate locations from which you choose to install or not a charging infrastructure. Can you tell us a bit about how you chose your candidate locations? You also showed a bit on demand coverage and how it is very dependent on this candidate locations and on the power power charging capacity in order to address demand satisfaction. So in your study, did you find like locations? Is the candidate solution has a huge impact on the solution, or what do you think about it?
Yeah, thank you for the questions, Reem. Donc first, for your first question regarding the candidate locations, as I mentioned maybe quickly during the presentation, actually at Paris-Saclay area, there are some charging stations. So we have already some candidate locations that are well prepared to accommodate chargers. So we considered these locations in the first step, but for sure now we consider fast chargers. So we have increased a bit the charging capacity of these locations. So this is the first type of location. The second type was for the service and gas stations that we have quite many on highways at Paris-Saclay area. So the idea was, why not, as they are perfectly located on the highway network, and as they are already service stations, so they are ready to adapt electric charging maybe in a few years' time. So we considered them as well as candidate locations. So these are the two types of locations that we have considered in this study. For gas and service stations, that we considered only those that are within 10 kilometers of an highway. So we don't go very far inside the city. It's just the highway network that we consider. Regarding your second questions, the candidate locations has a great impact on the demand coverage rate, because we had this issue quite often during the study, is that we have some locations with a very limited electric capacity. So we had to look for each location, we have to look for the capacity provided by the electric grid. We got some information from the Communauté d'Agglomération Paris-Saclay. We have also some information from the RTE website, which provides some information about the capacity provided. So we had to limit the number of chargers at some points because we have no more electric capacity to accommodate them. And that was reflected in the results, because we saw that some passes were really bad, poorly covered, let me say. So that highlights the importance of either adding new points at some highways or to increase the electric capacity if possible, either from the electric grid or by providing some photovoltaic power.
Okay, thank you very much, Aboud, for your answers. Benoit, can you talk to us?
I hope so. Can you hear me?
Excellent. So I suggest questions to be asked for Aboud and Marc-Olivier, if there are any by the participants. And now we will be back to our program with the presentation of Benoit, and we'll get back to the Q&A later on.
Yeah, sure. Well, thank you very much. I'm so sorry again for this.
No problem. So 15 minutes presentation.
Yep. So thank you, Rim, for the introduction. And good morning, everyone. So this is the last year of my PhD under the supervision of Yezekiel from Avignon University. and Olivier Alban and Jean-Baptiste from EDF. And I've been working on optimization of both the driving and the charging strategies for electric vehicles, which are coupled in urban environments. And today I wanted to show you the basic principles of our model on a specific example of which is commuting. But first, I just wanted to emphasize the particularity of our work, which takes into account both the electrical system, but also the transportation system when looking at electric vehicles. Because different operators coming from those two systems may have different objectives. For example, in the transportation system, you may have a local authority who wants to reduce traffic congestion, while in the electrical system, maybe the generation operator wants to reduce fossil fuel backups. And at the interface of those two systems, there are the charging station operators who want to ensure quality of service. And so the incentives they use to achieve these goals will impact actually both systems. Incentives like smart charging or bans of polluting vehicles inside city centers or public transportation. For example, the bans of polluting vehicles obviously will impact the transportation system, but also the electrical system, because the electric vehicles will be more likely to charge in the city center because it is empty. And this coupling between the two systems is really what the aim of my PhD is to try and model this coupling. So the use case I'm talking about today is about commuting. So we consider a group of vehicles, both either electric, EV, or gasoline vehicles, GV. So they live in a suburb area denoted by point O in the figure, and they want to drive to work, which is located in a city center at point D. And they drive past a hub. And at this hub, they have two possibilities. So either they can park their vehicle at the hub and charge their vehicle there, noting that the hub owns photovoltaic or PV solar panels, and then those commuters will take public transport to get to their work, or the vehicles can drive all the way to the city center. Okay, and in this presentation, I simplified the operators' interactions. So you still have the transportation network operator, which in our case can change the public transport ticket fare. But on the other way, you have only, we assume there was only a unique operator who was in charge both of the electrical systems, but also in charge of the hub. So this operator will schedule the charging operation of electric vehicles by making in order to minimize the grid costs. And after doing that, the operator will set an incentive smart charging price, lambda E, which will be a function of the total charging need at the hub, capital LE, and of the amount of solar panels, PV, at the hub. So these two operators need a model of the electric vehicles in order to design their incentives. And for that, we used game theory, where we suppose that all electric vehicles are rational and will will try to minimize their costs. So what are their costs? So the two choices they have are either choosing the public mode, meaning they arrive at the hub and pay for the energy they consume to get to the hub, and then take public transport. Or there is what we call the private mode. So they just drive into the congested city center and pay then for the total energy consumed. So more precisely about the costs, for both transport modes, you have two types of costs. The first one is travel duration, so which is assumed constant for the public mode in the public transportation, but which depends on the number of vehicles in the city center due to traffic congestion for the private mode. And you have the second type of cost, which is consumption cost, which here at the hub for the public mode depends on the number of vehicles charging at the hub, while it is supposed constant for vehicles who charge in the city center at point D. Okay, and then the solution of this game is not that easy. Vehicles, it's more difficult that all vehicles choosing the cheapest transport mode, because of the congestion phenomena, both in the city center or at the hub. But they still reach an equilibrium, or Nash equilibrium, where actually no vehicle can reduce its costs by choosing the other transport mode that it chose. Okay, so this is really the result of our model. Now, the next two slides, I wanted to emphasize on the charging unit price lambda E, which is at the hub, which is the specificity of our work. So, but first, before that, the hub operator needs to schedule the charging operation of electric vehicles at the hub in order to minimize grid costs. So we consider the vehicles which chose the hub to charge, and their total the charging LE aggregated over all these vehicles. Then these vehicles will stay at the hub for all the working hours, and the hub operator will try to find the optimal charging profile, the optimal aggregated energy to charge at each time slot T, in function of the PV production profile during these working hours. And so the grid costs here are really simply modeled by a quadratic function of the total load at each time slot. And just note that if at one time slot there is more PV production than EV charging need, then the grid cost is supposed no. Okay, and so the solution of this scheduling problem is really simple, especially if there is enough PV production during working hours to ensure the charging need LE. So this is you can see it's represented by the bars in red in the figure, and which leads to a zero grid cost G star. Otherwise, if the total charging need is greater than the total PV production, well, the optimal charging profile is should simply follow the variations of the PV production. So after having done that, the operator will make electric vehicles pay equally for the grid costs associated to the charging operation. So the charging unit price lambda E at the hub will be more or less G star divided by LE. And I wanted to give you an illustration of this charging unit price. So during year 2014, where we had some data on solar production around Paris, and you can see that the charging unit price is cheaper between March and October. But the charging unit price also not only depends on the PV production, but also on the number of vehicles charging at the hub. And this is what distinguishes the two curves. So in blue, in fact, you have twice as many electric vehicles at the hub than for the orange curve. And well, you can see that the more EVs there are at the hub, the more expensive the charging unit price is. Okay, so this is it for the model. Now I'll go on to the numerical results. First, a real simple illustration of the equilibrium concept, the equilibrium happening between vehicles. So for this, we considered the transportation network operator, which remember changes the public transport ticket fare TPUB. And so for each ticket fare value, we computed the corresponding equilibrium reached by the vehicles. So the figure in the figure, the blue curve represents the proportion of electric vehicles which choose to charge at the hub rather than driving into the congested city center. And in orange, you have the same, but for gasoline vehicles. Okay, so you can just see that the more expensive the ticket fare is, the less vehicles you have at the hub. But an interesting fact was that there is always more electric vehicles than gasoline vehicles at the hub. And this is thanks to the charging price incentive. Okay, and finally, the last result was I wanted to show that our model of electric vehicles can tell the hub operator how much solar panels it should install. So for this, we need to model the hub operator payoff, which is made of an initial investment in the solar panels. And we consider it during a period of time T, which might correspond to 20 years, for example. And during these 20 years, we consider the daily revenues from EV charging and the daily grid costs. Okay, and then what we did for each PV nominal power installed at the hub, we computed the corresponding equilibria during 20 years and the corresponding then payoff of the hub operator. And so we get this figure. And the only thing we can say is that for only the first solar panels are profitable because the grid costs avoided thanks to those solar panels compensate for the initial investment. Okay, and I think I'm done here. So thank you very much for your attention. And again, sorry for the little problem at the beginning.
Okay, thank you, Benoit. Since there are no additional questions for Aboud and Marc-Olivier, I think if you have any questions for Benoit, you can ask them now. I probably have one regarding the price of energy. So is it something that is how do you imagine it in a real setup? Is it something that since it's dependent on the EV number, is it something dynamic, or is it something that will be announced beforehand for the EVs? How do you see its application?
Yeah, that's a very good question, because that's the turning point of my PhD is because it's really theoretical for the moment. We wanted really something theoretically optimal in the sense of the grid. And to make it realistic, I think we've thought about making the. You have to remember that the electric vehicles are really rational and smart in our model. So we could think about maybe in each electric vehicle you have a numerical platform where the driver indicates his path, driving path, and charging need, and this way the hub could make all these computations I introduced, and then give back some charging unit price so that drivers could make better choices.
Okay.
Or something like that. Yeah.
Thank you. I don't know if participants have other questions. Okay. Thank you, Benoit, again for your presentation.
Thank you. I'm really sorry again for the bug.
No problem. Amira, the floor is yours for the last part of this webinar.
Yes, thank you all. Thank you, Rim, for the animation. Thank to all the participants to our event. It was really, really very interesting. I will not be long, so I will give you some takeaways. I've seen that a question was about the slides, the availability of the slides. We will ask each of the speakers if they are okay with that or not, and then we will make them available on the IRT site in the program. Now, this is for the availability of the slides. We also want to give you the opportunity to download our thematical leaflet. You can see now like a pop-up. You can download the brochure where you can see all the some projects that we are making about energy, electric mobility, and territories at IRT Systemix. So please check this out, and if you have any other questions or willing to work with us, just let us know. Now I will conclude that we will invite you to an event for the 3rd of June, which is the EDD at Systemix, which is the sustainable environment at Systemix, where we will share our works and our thoughts and our partners' thoughts about the thematic of the circular economy and the ecological transition. Again, thanks to VDECOM, EDF, Boston University, also to Aboud from Expleo, thanks to Central Supélec, and finally IRT Systemix for the organization. See you soon, talk to you soon. Do not hesitate to write to us. Okay, this will end the presentation and all the event. I wish you all a nice day.